Welcome to EPG Pathshala in Computer Science. This is a series of lectures in computer networks. So, we have been looking at the protocols that are used in wired networks. Starting from today, we will be looking at wireless networks. So, we will look at different protocols that are used in the wireless world. Now, the importance of wireless networks need not be emphasized. We all know that we all have many more mobile devices, many more wireless devices rather than the wired devices. The number of wired devices and cell phones and the wireless devices, cell phones, laptops and other things are increasing. So, we are all very much aware of that. So, definitely there is a necessity to learn and to know how these are integrated into the wired network, into the network as a whole. So, to start with, we will take a look at the different characteristics of wireless networks, and then we will look at some of the standards for wireless networks. In this module, we will cover Wi-Fi, which is the LAN standard, which is the wireless LAN standard, which goes by the name of IEEE 802.11. So, we will look at the details of that particular protocol. Okay. So, when we talk of wireless links, we know that wireless links transmit electromagnetic signals. It could be radio frequency signals or microwave signals or infrared signals. So, these are different possibilities that we have. And wireless links typically are all, they share the same media, right. So, that is the, it is a broadcast media that is used. So, everybody has to share that same media. So, the major challenge that we have when we talk of wireless networks is how efficiently we are able to share this media without having some undue interference between one another, okay. So, that the different devices which are transmitting do not interfere with one another. So, we need to figure out mechanisms by which that interference can be minimized. Normally, the sharing is accomplished by dividing the media either along the dimensions of frequency or space, okay. This is typically what we do. And of course, time also is another factor. So, we could do either time division multiplexing or frequency division multiplexing or space division multiplexing in order to share the available media. Okay. And normally what happens is that when we have exclusive use of a particular frequency in a particular geographic area, that is allotted to an individual entity or a corporation, that is done normally by means of some government agency. So, we normally have a lot of regulatory factors that need to be taken into account in terms of what kind of frequencies are allocated for different users or different technologies to use the radio frequencies available as such. Okay. So, there are some, for instance, there are some special bands are reserved for certain purposes or certain uses. So, you cannot use those for other purposes. So, we need to be aware of this space that is available, of the different spectrum that is available and how the spectrum actually gets shared for different purposes by different users. So, that is just an overview of what we need to remember about wireless links, and we are familiar with most of these points that we just talked about. Okay. So, now if you look at the elements of a wireless network, this is also something that you would be very much familiar with. So, if you look at the devices that we have wireless hosts. So, wireless hosts could be laptops, smartphones, and they would typically be running applications. They may be stationary or mobile. Now, remember that wireless does not always mean mobility. It could be a stationary device just connected by means of a wireless connection, okay. That is a possibility. So, we have wireless hosts, and we always have some kind of central devices which normally go by the name of base station. So, typically these base stations would be connected to a wired network. So, they are responsible for sending packets between the wired network and the wireless network, okay. So, they will have a responsibility for a particular area. So, they are responsible for taking packets that are there in their area to the wired network. So, for example, your cell towers, your 802.11 access points, depending on what kind of wireless technology we have, there are different names that are given to these central or these infrastructure kind of devices that we have. So, they take the responsibility of connecting up the wired world and the wireless world. Okay. Then of course, we have wireless links. So, these wireless links are the ones which are used to connect the mobile devices to the base stations. So, they can also be used as a backbone link, and normally we have some kind of a multiple access protocol that is used to coordinate access to the links, and it could be supporting various data rates depending on various factors, transmission distance and so on. Okay. So, that again would depend on what kind of links are used and their characteristics. And there are normally two modes of operation that we normally talk about when we talk of wireless networks. One is called as the infrastructure mode of operation, and the other is called as an ad hoc mode of operation. So, when we talk of infrastructure mode, we typically are looking at a situation where there is a base station which connects the mobiles into a wired network. Okay. So, you could have some kind of handoff mechanisms which are used when a mobile changes base station, it goes from one base station to another, and you will still be able to maintain the connectivity with the rest of the network. So that is facilitated by means of the base station. So we have some infrastructure, some specific devices which are responsible for providing the connectivity and for providing the routing functions and so on. So that is what we mean by an infrastructure mode of operation. So when we talk of an ad hoc mode of operation, here there are no base stations. So there is no specific infrastructure available as such. So which means the nodes can just transmit to each other when they are within the coverage region of one another, or the nodes themselves must organize themselves into some kind of a network, and they should take responsibility of routing packets among themselves. So which means a node will act not just as an end node but also as a router. So this is called as the ad hoc mode, and we talk about networks which are formed in such a manner as ad hoc networks. So we talk about mobile ad hoc networks and so on. So these are the two different modes in which wireless networks could be set up. Okay. Now if you look at the common wireless technologies that are used, depending on the range that is covered, depending on the data rates that they cover and so on, there are many different technologies that are used. So we will look at three distinct categories. So we have the Bluetooth wireless technology, which is used typically for short ranges, typically within about 10 meters distance. Data rates that are supported are 2 megabit per second. Typical use is for to link a peripheral to a computer, okay? And the wired technology analogy for this would be something like a USB. Okay. Then we have Wi-Fi, which is the wireless LAN. So here the coverage is much larger, up to 100 meters can be covered, and data rates are about 54 megabit per second shared, and this is used to link a computer to a wired base. Again, the wired analogy for this would be Ethernet. So then you have 3G cellular or 4G or whatever, cellular technology as such. So this is used for a much larger coverage, tens of kilometers and hundreds of kilobits per second per connection. And now if you talk of 4G and so on, it is all in terms of megabits and hundreds of megabits and gigabits, and that is the kind of data rates that you can support. So these are normally used to link a mobile phone to a wired tower, okay? And a wired technology analogy for this would be DSL. Okay, so this is these are different technologies that we have. So what we will actually be doing is we will take each of these and we will be looking at each of these in detail. So we will look at the Wi-Fi specifically in this particular module. Okay. So in general, this is again placing the same wireless link characteristics on a in a comparative scale. So you can see that indoor 10 to 30 meters, typically we have different protocols that are used for that range. You have the 802.15, which is a Zigbee protocol. Then you have 802.11 N, A, G, B and so on, and you can see that they support different data rates. Similarly, for wireless and for cellular technologies, we have CDMA, GSM, 2G, 2.5G, 3G, 4G and so on. You can see that here you can see that as we go from one generation to another generation, the data rate that is supported is increasing, and you are able to support much larger distances. So you can go from outdoor from 50 to 200 meters to mid-range to long range, okay, up to 20 kilometers can be supported using these. So these are the different wireless technologies that we have today, and there are a lot more that are coming up, okay. So as the technology advances, we find that new standards are coming and we have new applications which demand a higher and higher data rate. So it's kind of a very positive feedback which kind of pushes the whole thing further and further. Okay, so now coming to the normal characteristics or in a sense challenges that we need to face when we talk about wireless links. Okay, we need to understand the major differences from the wired link. See, one of the important differences is that the decrease in the signal strength. That is, when a radio signal, as it propagates and as the distance increases, it attenuates as it propagates through the matter, right. So there will be something what we call as a path loss. That is, there is a loss along the path. Now this need, of course, there may be some attenuation in wired networks as well, but in the case of radio signals, it is much more accentuated. Now you can also have interference from other sources. So we know that there are standardized wireless network frequencies. For instance, 2.4 gigahertz is shared by other devices as well. So phones, for instance, devices, for instance, some motors, they all have the same frequencies, though these could interfere with the transmission at a particular frequency band. So another problem that we face when we talk about wireless transmission is the multipath propagation issue. So basically what happens when you send when you have radio signals that are transmitted, these radio signals can reflect off various surfaces. They could reflect off the objects on the ground, okay. So which means it could, so these reflected signals would appear at the destination at slightly different times. So which means that when they the same signal reflected by different objects when it appears at a particular, at the destination, when all of them put together, it looks like it's a noisy signal, right? You have a lot of interference because of these reflected waves that are coming in. So that is something that we need to handle. Okay. So all these put together, they make communication even for a point-to-point wireless link much more difficult. Okay. So that's the challenge that we are that we need to handle. Okay. So another important aspect that is the signal to noise ratio. So now signal to noise ratio, remember, larger the signal to noise ratio, it is easier to extract the signal from the noise. Okay, it's a good thing. So, and if you look at how signal to noise ratio varies and what is the effect of signal to noise ratio vis-a-vis the bit error rate. Now, given a particular physical layer, okay, if you increase the power, okay, you would be able to increase the signal to noise ratio, because when you say increase the power of the signal, obviously the SNR will increase. And when you increase the SNR, you would be able to decrease the bit error rate. Okay, so which is also a good thing. So, but we need to increase power. So that becomes one of the issues that we need to consider. And so, given a particular SNR, signal to noise ratio, another option that you could have is that you can choose a physical layer that meets that particular bit error requirement, which gives the highest throughput. So, for instance, if you look at what we have here, you can see that as the this is for BPSK, for instance. BPSK, as the SNR increases, we can see that the bit error rate, right, also increases. So, you can see that that you get a much better bit error rate as bit error rate decreases, right, because 1 in 10 power minus 2 when your SNR is low, but when your SNR goes towards 10, you can see that the bit error rate becomes about 10 power minus 7. So, which is much less of bit errors that are occurring. So, as the SNR increases, you can see that you have change in the bit error rates. So, what we could do is, if I have a particular SNR that I am allowed to use, I can choose the appropriate physical layer technology. I can use QAM256 or QAM16 or BPSK, depending on what SNR is available for me, in order to meet a particular bit error rate requirement. Because in some cases, you may be able to work with higher bit error rates. In some cases, you need a lower bit error rate. So, you need to choose the SNR and choose the physical layer appropriately. Okay, that is important. And what is also important to remember is that the SNR may change with mobility. So, which means we need to be able to dynamically adapt the physical layer as you move. On the move, you must be able to adapt these things. So, the modulation technique, the rate, these things you must be able to change in order to take care of these things, right. So, that is another challenge that we have. So, in general, if you look at the network characteristics, now we talked about link characteristics. Now, when you look at a wireless network characteristic, what we find is that there is an additional challenge that comes just because of the fact that we have multiple wireless senders and receivers which are transmitting data. Okay. So, when you have multiple access, right, so that causes additional problems. One of the very common problems that we talk about is the hidden terminal problem. So, this is a situation where, for instance, you have these 3 nodes B, A, B and C. So, let us say B and A can hear each other, B and C can hear each other, okay, but A and C cannot hear each other, which means if C is transmitting to B, A will be unaware of it, and A transmitting to B, C is unaware of it. So, what could happen therefore is, if A and C simultaneously transmit to B, being unaware of the fact that somebody else is already transmitting the data, so naturally there will be interference at B. So, this is something that we need to avoid. So, we say that A and C are hidden with respect to each other. So, we have a hidden terminal problem. Okay. So, similar, I mean this is accentuated by the fact that you have signal attenuation. So, this the same thing could happen because of the signal attenuation. So, A's signal strength, for instance, is such that when it goes to B, B can hear it, whereas by the time it goes to C, the signal strength is so low, C cannot hear it. So, same thing happens with respect to C. C's signal strength is decipherable at B, but it is too low at A. So, naturally what happens? A and C cannot hear each other, and that causes the interference at B, right. So, this hidden terminal problem occurs because of these kind of reasons. So, this again is a problem that we need to handle. So, this is causing an interference, this interference will have to be handled. Okay. So, now we will look at the IEEE 802.11 wireless LAN protocol and see how these different problems are handled by this particular standard. Okay. So, if you look at the 802.11 standard, there are multiple versions, or so to say, of this particular protocol. You have the 802.11b, which basically operates in the 2.4 to 5 gigahertz unlicensed spectrum. You get data rates of up to 11 megabit per second. It uses what is called as direct sequence spread spectrum at the physical layer, okay, and where different hosts use the same chipping code in order to transmit their data. Then we have 802.11a, which works in the 5 to 6 gigahertz range. You can have up to 54 megabit per second data rates. 802.11g, 2.4 to 5 gigahertz range, up to 54 megabit per second. And then 802.11n, where you use multiple antenna, and therefore you can have up to 200 megabit per second and so on. Now all of them use a particular technique called CSMA-CA for multiple access, and all of them support both the infrastructure mode of operation, this is the base station mode of operation, and an ad hoc mode of operation that we mentioned, right. So this is basically, so we need to understand what the CSMA-CA is. That is the key multiple access protocol that is used in 802.11. We will look at that shortly. Okay. So if you look at the 802.11 wireless LAN topology, so it basically looks like this. You have access points. So these access points are connected to various mobile stations, and this access point along with the mobile stations that it connects to are referred to as the basic service set. Okay. So you could have one basic service set here, another basic service set here, and these access points would be connected by means of what's called as a distribution system. So this distribution system could be any type of LAN, for instance. So you could also have an access point which is not connected to a distribution system, which is just connected to a set of nodes, an independent basic service set as such. So this would form an ad hoc network. So you have an infrastructure based network here, and you have a ad hoc network that is available here. So you could have both modes of operation that are supported by 802.11. Okay. Right. So if you look at the protocol layers, how the 802.11 protocol layers work. So at the physical layer, 802.11 can work with various physical layer technologies. It could be frequency hopping spread spectrum which is used, or direct sequence spread spectrum, or it could use IR, infrared, or OFDM, which is orthogonal frequency division multiplexing. So all these are different physical layer technologies that are supported. We are now more worried about the MAC layer. So it has a 802.11 MAC layer, and it has a 802.2 LLC, logical link control layer, that is supported. So these are the layers that we need to understand about 802.11. So if you look at the wireless LAN evolution in terms of speed and functionality, so initially your 1 and 2 megabit per second was supported using IAR, DSSS and FHSS, and then later it is moved up from 5.5 to 11 megabit per second and all the way up to 300 megabit per second. Okay, so this is possible in 11N with multiple input, multiple output OFDM kind of physical layer technologies that are supported. And in terms of functionality, we also have improvements that have happened with the evolution. So for instance, 802.11e supports quality of service, 802.11i has enhanced security features, 802.11s supports mesh, and 11K and 11R support roaming and measures and handoff features that are supported. Okay, so these are the evolution that has happened on the wireless LAN 802.11 related protocols. Okay. So now coming back to understanding the functions of this 802.11 architecture. So as we said, you have base stations or basic service sets which are connected to a base station. Nodes, that is nodes which belong to a particular area, which are connected to a single base station or an access point, they form the basic service set. So these basic service sets could be connected, as we said, by means of any network. It could be a hub or a switch or a router also, which connects it to the internet. So this is what you would have. So in infrastructure mode of operation, as we saw, you would have wireless hosts and an access point. If it was an ad hoc mode, it will only have hosts. So that is something that we already saw. Okay. Now, one of the important aspects that we need to understand here is, the first thing that we need to understand, so to say, is how is it that you have the association of the nodes with the access points taking place. Okay, that's something we need to understand, and we need to understand what channels will be available for these nodes to be able to associate with the access points. So if you look at 802.11b, for instance, the 2.4 gigahertz, 2.485 gigahertz spectrum that is available to it is divided into 11 channels at different frequencies. Okay, and the access point administrator chooses a particular frequency for the access point. So interference is possible because that same channel could be used by some other neighboring access point. So we need to be careful about that. And what a host must do is, a host must associate with an access point. So how would it do that? It would normally scan the channels. Now it knows that there are 11 channels at different frequencies. So it will scan these channels, listening for what are called as beacon frames, which contain the name of that access point, name, or what we call as the SSID, and some kind of an identifier, and a MAC address. So once it gets this beacon frame and it identifies that there is a access point available, it now will have to select one of those access points to associate with. Then it can perform some kind of authentication mechanism. So that it will be able to connect to that. Once it is connected, it can run DHCP to get the IP address in that AP subnet. That AP will be connected to some subnet. So now this device will be able to get an IP address in that particular subnet. So this is what we expect to normally happen. Okay. Right. So when we talk about this scanning, right, there are two modes of operation here. We talk about what's called as passive scanning and active scanning. So in passive scanning, what happens is that when a node wants to connect, it waits to hear beacon frames from the access points. So the first step here is the access points sending frames to the sending the frames. Okay, so beacon frames are coming from the access points. This is one. Now second step will be, now on hearing these beacon frames, by looking at either signal strength or whatever basis, the host H1 chooses which access point it wants to associate to and sends what is called as an association request frame. So for instance, the H1 here may send a request frame to this access point here, right, so AP2. So now what will happen when it sends this association request, that access point will send back a association response frame, right, saying that yes, you are now associated with me, right. So that will be the third step. So this is what is called as passive scanning, because the host here is passive with respect to the host. Host is really not doing anything specific, it is being passive. So next is an active scanning mode. So in the active scanning mode, for what happens is that the host starts off looking for access points. So what the host will first do is send out what is called as a probe request frame. So it broadcasts this probe request frame, okay, sends it all over. So all the APs which listen or which receive this probe request frame will send a probe response frame. So you can see that host is broadcasting probe request frame, step 1. Step 2, it receives the probe response frames from these. Now out of these two, it selects one access point that it wants to connect to, maybe based on again signal strength or whatever reason, and it sends an association request frame to that particular AP. Now that again will send back an association response frame and the association gets completed. Okay, so these are the two modes, passive mode and active mode for getting connected to the network as such. Okay. So now when we have multiple devices accessing the network, right, so let's look at what are the other things that we need to deal with. So one of the things that we need to deal with is when more than two nodes are transmitting at the same time, we need to avoid collisions. So how do we do that? Okay. So first thing of course we will do is we will do a CSMA technique, which is very similar to what we have in Ethernet, that is the CSMA part. The carrier sends multiple access, that is you will sense the carrier before you transmit. So there is already some transmission going on, obviously we do not want to transmit at that time, right, you do not want to collide with an ongoing transmission. So you will sense the medium before you transmit. So if you sense the media and then if you find that there is no transmission, then you could transmit. Okay. But the difficulty in 802.11 in a wireless network as such is that you cannot do collision detection as is done in the case of Ethernet. In Ethernet for instance, we do the same CSMA, but when we transmit, we do a collision detection. If two people have transmitted at the same time, we will detect the collision and you will be able to back off based on that. But in the case of wireless network, it becomes difficult to sense the collisions. Okay, that is because again as we saw, it could be because of reasons like fading, right, the attenuation that is happening of the transmitted signals, okay, and we also looked at the hidden terminal problems. You can't sense all collisions, right, so it could be because of the hidden terminal problem or because of the attenuation of the signals. You can't really see if A is transmitting while C is transmitting data. C cannot hear A's transmission, right. So we need, you can't do collision detection, so we need to do something else. So what do we need to do? We do what is called as collision avoidance. So we have a technique called CSMA-CA, the C for the collision, A for avoidance. Okay. So how do we avoid the collisions? So that's the important part of the 802.11 protocol. So what we do here is, the idea that is used is that you would like to allow the sender to reserve the channel for some amount of time rather than do a random access of the channel. Okay. So you want to avoid collisions of long data frames. So how do we do that? How can I reserve the channel? So this reservation is done by means of what is called as sending a small packet, okay, what is called as a request to send packet. So the sender, before it starts transmitting, will send out first something called an RTS packet or a request to send packet using the CSMA mechanism, that is the carrier sense multiple access mechanism. Now RTS which are coming from two, now you can always ask this question, right. So there can be two nodes which are sending RTS at the same time, so those could collide. So if they collide, what will happen? Obviously, we have a collision again. So what is done in that case is that you will again have to retransmit the RTS. So that's something that which will have to be done. But our the difference we have is that these RTS frames are very short. So this collision will also be only for a very short period of time. Now what happens when the RTS is sent is that the base station on receiving this will send a clear to send in response to the RTS. That is, the receiver will send a clear to send saying I am now willing to receive your data. Now this RTS and CTS will consist of information which says that I am going to transmit to you for this much amount of time. And the CTS will say yes, you can transmit to me for this much amount of time. So which means all the others who listen to this CTS will know that this particular sender is sending data to this receiver, and all the others will defer their transmission for that particular duration of time. So they won't interfere with that transmission, right. So in a way you can see we have reserved the channel by sending this special packet called the RTS packet and receiving the CTS packet as a response or an acknowledgement for that RTS transmission. Okay. So you avoid data frame collisions completely using these small reservation packets. That is the idea that is used. Okay. So this is basically how it will work. So let us say for instance A and B want to send data. So this sends an RTS, this also sends an RTS, a collision could occur. So a reservation collision occurs. Now what will happen? Both A and B won't receive their CTS. So they will wait for a random amount of time, and after a random amount of time one of them, let us say, sends an RTS. So A sends an RTS. Now when A sends an RTS, the access point will respond with the CTS. Now access point's response will be heard by both A and B. So now B will refrain from transmission and A can start its transmission. Now A sends its data, right, and until the access point acknowledges that, the other stations, B for instance in this case, will defer transmission and it will try to access the channel only after this point of time. So you can see how the RTS-CTS exchange helps to avoid the collision. So this is the key technique that is used. So normally what we have is that we have this 802.11 sender which will sense first the channel, right, and along with the RTS and CTS mechanism there is also another mode of the CSMA mode of operation that we said, right. So what happens in that mode is that the channel will first sense the, sender will first sense the channel and he will normally wait for a certain amount of time, what is called as the interframe space. We have different interframe spaces which are used to space out the transmissions of different users for different purposes. So there is something called a DIFS, a distributed interframe space, a timing that is used by the sender for which he will wait before he will transmit the data. Okay. So now he transmits the data and on receiving the data the receiver will wait for again a short IFS amount of time before he sends back the acknowledgement. Okay. So now if the channel is sensed busy, what is it that the sender would do? The sender would start off a random back off time and it will start off a timer which will keep counting down until the while the channel is idle, and it will transmit when the timer expires. Okay. So if there is no acknowledgement, what does it indicate? It indicates again that something went wrong with the transmission. So then it will have to repeat the transmission. Okay. So that is what it will happen. So this is the CSMA part of the transmission, that is without the collision avoidance part. Okay. So that is what you will have to do over here. And 802.11 receiver, it would if the frame is received, fine. If it does not receive the frame, right, if it has received the frame correctly, it sends back an acknowledgement after waiting for this SAFS amount of time. Okay. Why do we need this ACK? Because we know that there could be hidden terminal problems if when you are not using the RTS-CTS mechanism. So then we need to handle this. Okay. So we have the CSMA part and then we have the CA part. So combine these two together and you get your CSMA-CA mode of operation as such. So now when we talk of 802.11, it actually supports two modes of operation. One is called the DCF mode of operation, another called the PCF mode of operation. DCF stands for distributed coordination function, where it uses the CSMA-CA approach, which uses both the physical and the virtual carrier sense. Physical carrier sense is the CSMA that we talked about, virtual carrier sense is the RTS-CTS mode of operation that we talked about. Okay. Then we have a point coordination function where the, so you can see that in DCF actually what happens is that it is a free for all, anybody can transmit to anybody at any point of time. So it is a completely contention based mechanism of getting access to the channel. Now in the point coordination function what we do is the point coordinator typically, which is the access point, that access point acts as the arbitrator and determines who will actually get to transmit at a given point of time. So what the access point will do is it tries to provide a contention free mechanism of data transfer. So it will poll the stations and let the stations find out which are the stations that need to transmit, and give the channel to those stations in order so that they can do the transmission. Okay. So we have these two modes of operation, PCF mode and the DCF mode, and both these kind of coexist in a given 802.11 network. So basically the way it is done is that if you look at the complete data transfer, what we call as a super frame structure for the data transfer, you will find that some amount of, there will be a beacon frame that is sent, which is used to indicate the beginning of this particular transmission period. Now for this entire transmission period, after the beacon frame, there is something called a point coordination function time that is specified. So this is a contention free period. Then there is a DCF transmission that is supported, which is called as the contention period. Okay. So normally the sequence will be like this. So the PC first, the point coordinator or the AP will send out a beacon frame to reserve this contention free period. So the duration for which it wants to access, that will be first reserved by it. Then the stations will set their what is called as a network allocation vector to reserve that particular point coordination function for that particular time. Okay. Now they will be able to transmit for that duration of time. After that, the PCF will be followed by a DCF period where it is a contention based period. So anybody who wants to transmit will first go through the CSMA CA mechanism, and they will try to transmit the data. Okay. So CFP repetition period. Now while the DCF transmission is going on, if the CFP repetition period ends, you cannot immediately start because something is happening, right. So if it is busy, you will delay this period for a while, and then once the transmission is over, then you start the next CFP repetition period will start. Okay, that is basically how the DCF and PCF are used together. So this basically tells you how the DCF transmission takes place. You are checking whether the channel is busy, you wait for interframe space, you have a back off timer, you generate a new back off time, wait for the back off time, start transmit. Okay, if the ACK is received, fine, successful transmission, otherwise you increment the number of attempts, and if it is too many attempts, you say that the transmission has failed, otherwise you go back and transmit the whole thing. So this is what happens on the transmitter side. On the receiver side, similarly you check whether the channel is active, you start receiving. If it is still active, you continue receiving. If the receiving frame is too small, then you know that something is wrong, so you go back to channel active. If you recognize the address, yes, fine, otherwise you go back again. And then you check whether it is a valid FCS, if things that is your, if it is a valid frame, then if it is yes, you continue, send the acknowledgement, and your reception is successful. Otherwise, you will have an error, so you indicate that there is an error. Okay, this is the structure that we have in DCF. Now coming to the frame structure, this is another very important aspect of the 802.11 frame of the protocol. Now if you look at the frame structure, you will see that there is a frame control field, a duration field, and then you will see that there are 4 address fields, address 1, address 2, address 3 and address 4. Now normally you would have seen that in all the protocols that we have, there will be 2 addresses, the destination address and the source address, but here we have 4 address fields, and then there is a sequence control field, then of course the payload and then the CRC. Okay. So if you look at these 4 address fields, you see why we need these 4 address fields. So the address 1 is normally the MAC address of the wireless host or the AP, which is to receive this frame. Okay. Address 2 is the MAC address of the wireless host or AP, which is transmitting this frame. Now the address 3 is the MAC address of the router interface to which this AP is attached. So remember that this AP will be attached to some, could be attached to some router. So in which case you may want to send a packet into the network, so which means you need to go through the router. So to go to the router, you have to go through the access point. So from here you go through this access point to that particular router. So that information can be specified here. Okay. And this address 4 is used only when you are in the ad hoc mode. So this is typically used when you have one access point connected to another access point. So you may have one device going from one access point's area to that access point AP1, let's say, from that to AP2, and from AP2 to the destination. So you can see that there are 4 addresses that are required. So that's where this 4th address will come into play. Otherwise, if you are connected to a router, this access point is connected to a router, this is the 3rd address that we will need. Okay, so this is the purpose of the 3 addresses that we have over here. So you can see how the addressing will be. So this, when your H1 is connected to the access point, address 1 will have the AP MAC address, that is the destination. H1 MAC address is the source, and the 3rd address will have the R1 MAC address. Now when this access pointing sending it to the router, it may be now sending it as an 802.3 frame. This may be an Ethernet network, right? So in which case So it will take this R1 MAC address, put as the destination address, use this H1 MAC address as the source address and send it over here. Okay, so you can see how this information will be used by the access point to forward it to the router. Okay, this is the important aspect of the addressing mechanism that we need to remember. Okay, and if you look at this frame control field in the format, there are a lot of information that we have over here. There is something called a type field. This type is used to indicate whether it is an RTS field, RTS packet or a CTS packet or an ACK packet or a data packet. And the duration here, this is the duration for which the channel is being reserved. Okay, that is used when you have an RTS, CTS packet that is being sent. Okay. And then there are a few other fields that we have which are used for power management, more data, for security purposes and so on. So, many other fields are also used over here. Now, there are also certain advanced capabilities that 802.11 supports. We will quickly look at just one or two of them. One is rate adaptation. That is, we said that if a mobile is moving away and its bit error rate, for instance, is not acceptable, so it may move to a different transmission rate. So, an example is what we can have, you can see over here. So, you can see that, for instance, here it may be moving away, so its SNR decreases, right. You can see that SNR is decreasing. So, when it decreases, what it could do is it could switch to a different transmission mechanism at the physical layer, right. So, in which case now the bit error, so you switch to a different one and use this particular transmission mechanism and choose the one that, and you will be at an acceptable bit error rate when you move to a different transmission mechanism. Or when I say transmission mechanism, what I am essentially meaning is that you can use some other modulation technique. So, we have QAM 256, QAM 16 and so on, right. So, you may move to a lower rate modulation technique and be able to still provide the service. So, this is one technique that is normally now provided on many of the 802.11 devices and networks. So, another capability that is also provided is for power management. So, here what normally a node can tell the AP is that I am going to sleep until the next beacon frame. So, which means the AP should not send any transmit frames, any frames to this particular node until the next beacon frame. So, when the next beacon frame comes, the node will wake up automatically and it will be able to receive the data. Okay. So, the beacon frame will contain the list of mobiles with the AP to mobile frames which are waiting to be sent, right. So, it will say these are the ones who are waiting for the data to be sent. So, the node will stay awake if there is a frame that is meant for it, that is there is some frame which is to be sent to it. Otherwise, it can sleep again until the next beacon frame. So, this way the devices can reduce the power consumption, okay. They can do the power management. So, this is also something which is now provided in 802.11. Okay. So, to summarize, what we have looked at with respect to 802.11 are the following. We looked at the characteristics of wireless networks, we looked at the CSMA-CA mechanism, we looked at PCF and DCF modes of operation, frame formats and different capabilities. Thank you.